Hello, everyone, and welcome. Thank you for watching this recorded talk for STOC 2023. My name is Kevin Rao, and I am going to be talking about faster Walsh-Hadamard and discrete Fourier transforms from matrix non-rigidity. And this work was done together with Professor Josh Alman at the wonderful institution, Columbia University. So, jumping right in, what are the discrete Fourier transform and Walsh-Hadamard transform? So these are both very important linear transforms. They're used in image, audio, signal processing, as well as they also appear in algorithms and complexity. So these transforms are both of great practical and theoretical interest. Both of these transforms are known to be computable in O of n log n time. And we improved the leading constants for these algorithms in this work. An algorithm that computes the discrete Fourier transform is called a fast Fourier transform, or FFT for short. And for both of these transforms, it is believed that they cannot be computed in little of n log n time, but this is still an open problem. One piece of evidence, though, that the Walsh-Hadamard transform in particular cannot be computed in little O of n log n time is that until now, there has never been an improvement on the leading constant for n log n. Until now, it's always been the same folklore algorithms runtime. But in this paper, we do improve on the leading constant. So a quick plan for this talk. The results in this work are a two-parter, so the talk will be as well. First, we'll talk about existing work and state results from before and state our results. And then we will first talk about our improved algorithm for computing the Walsh-Hadamard transform. And then we will talk about our improved fast Fourier transform. So here is a table of the history of the best FFT algorithms for n being a power of 2. And for the rest of this talk, n is always going to be assumed to be a power of 2, which is the standard assumption. In this table, the leading constant is the constant in the real operation count, which is also standard, and we will define it later in this talk. So the history of the fast Fourier transforms started in 1965 with the Cooley-Tukey algorithm, which is likely the one that people are most familiar with. And since then, there have only been 4 improvements on the FFTs, including ours. So despite the DFT being important for a really long time, not a whole lot of success has been made in improving the runtime for its algorithms. And the improvements shown in this table may look small, but for example, in the modified split radix algorithm is actually currently being widely used in many applications. So even these modest improvements are indeed very important for practical applications. The most recent improvement before ours was actually in 2017 by Igor Sergeev, but this algorithm is not widely used because there is no code implementing it, and it's only a theoretical optimization of a previous algorithm. And yeah, so the leading constant of C means C n log n plus lower order terms, real operations. And the lower order terms are all very small constants. For the Walsh-Hadamard transform, as I mentioned, until now, the best algorithm has always been what's called the folklore method, which is basically just following the recursive form of the Hadamard transform. It requires n log n, leading constant 1, field operations over whatever field you're computing over. And yeah, there has just never been any faster algorithm for computing the Hadamard transform. I would also like to mention that our approach for improving fast Fourier transforms is actually quite different from all the previous approaches. All the previous improvements shown in this table focus on the way that you multiply the complex constants that are involved when you compute a discrete Fourier transform. But our fast Fourier transform focuses on grouping additions and subtractions in an advantageous way that allows us to perform them more quickly. So the main results in our work are twofold, as mentioned, and n is a power of 2 always. So the first theorem here improves the leading constant of the Hadamard transform from 1 to 0.96 approximately. It's 23 over 24. And the theorem is given any field and an input from that field. we can compute the Hadamard transform on our input using our most 23 over 24 n log n plus 13 over 12 n field operations. And our second theorem is for our fast Fourier transform, and it's given a length and input x of complex numbers. We can compute the discrete Fourier transform over input using at most 15 over 4 n log n plus some lower order terms, real operations. And so for the Hadamard transform, we count field operations. For the discrete Fourier transform, we count real operations. And we will define real operations more concretely in a later slide when we get to it. So yeah, these are our major results stated in one slide. Now, the main ideas that we have for the aforementioned results are split between the two problems. For the Walsh-Hadamard transform, the main idea is to use the non-rigidity, which we will define as well, of the Hadamard transform to get an improved Hadamard transform, an improved algorithm for the Hadamard transform. And then for the discrete Fourier transform, we first find a reduction from part of the transform to the Hadamard transform. And this lets us isolate large Hadamard transforms in the process of computing a DFT. And then we'll use our faster Walsh-Hadamard transform algorithm on these isolated large Hadamard transforms to then get an improved fast Fourier transform. So first, going into the definitions regarding the Hadamard transform, a Walsh-Hadamard transform is defined here in its matrix form. A Hadamard matrix is defined recursively for n greater than 4 by this recursive form, where you have the base case of the 2x2 Hadamard matrix, and then for every larger Hadamard matrix, you basically just take the previous Hadamard matrix, write it 4 times, and negate the 1 in the bottom right-hand corner. And the goal of the Walsh-Hadamard transform is to compute y equals h of x for the input vector x. So you multiply the vector on the right side. And here we just have an example of the 8x8 Hadamard matrix. The folklore algorithm that I mentioned before just directly follows this recursive form that I showed that is shown on this slide. And you just compute the half-size subproblems and add and subtract the results. So here is the code for the folklore Walsh-Hadamard transform written out. As I mentioned, first, all you do is you split your input into like the first half and the second half. You recursively compute the Hadamard transform on those two halves. And then you just take those like length n over 2 vectors and component-wise add and subtract them to get your final Hadamard transform. So this is the most basic way to compute a Hadamard transform. And for a long time until now, this has just been the best known way to do it. And when you solve the recursive form for how many field operations it requires to compute this, you get n log n with a leading constant of 1. So some more background on ideas that we used for our improved Hadamard transform. We need to introduce the idea of rigidity. So a matrix is called rigid if you cannot change a small number of its elements to make it a low rank matrix. And in formal definitions, small number and low rank are parameterized, but for this talk, it's not super important to go into those details. In other words, a matrix is non-rigid if it can be written as the sum of a low rank and a sparse matrix. This idea of rigidity was introduced by Les Valiant in 1977 to prove lower bounds for linear transformations. In particular, if you prove that a matrix is rigid, you prove a lower bound on its linear circuit complexity. Unfortunately, proving matrices being rigid is quite hard, but we take kind of a logical converse of Valiant's statement, and we use non-rigidity of the Walsh-Hadamard transform, not the non-rigidity of the Hadamard matrix, to provide sort of the main source of inspiration for our improved algorithm. So we use an upper bound on rigidity the non-rigidity statement is an upper bound, and we use that to get a concrete algorithm for the Hadamard transform. And in particular, and this like low rank plus sparse matrix is called the rigidity decomposition of a matrix. And this is the rigidity decomposition that we use for our algorithm. It's for the 8x8 Hadamard matrix. And because we use the 8x8 Hadamard matrix in our algorithm, this motivates using what's called a radix 8 recursive structure, where we break our input into pieces of 1/8 size, compute on those pieces, and then we combine them back together in a structure that looks like the 8x8 Hadamard matrix. Notice here that the low rank matrix is rank 2. The top and left side are all ones. Everything in the middle is -1. And in the sparse matrix, we just have some 2 strategically placed in locations so that when you add these matrices together, you just get the Hadamard matrix. And because we're using the 8x8 Hadamard structure to combine our recursive calls, we are thus interested in how to compute the 8x8 Hadamard transform more quickly, because this would allow us to get an overall faster algorithm. Excuse me. So computing the folklore algorithm for the 8x8 Hadamard matrix requires 24 operations, n log n. When you plug 8 in for n, you get 24. But if we directly compute the aforementioned low rank and sparse matrices, if we just directly compute the 2 matrices involved in our rigidity decomposition, and then we add the results together, that would actually require 37 operations. So our rigidity decomposition at first glance is actually worse, but we have 3 key observations here, and I'll go into more detail on them in future slides. And these observations actually allow us to bring our operation count down and get a faster algorithm. So the first observation is that we can reuse intermediate computations, and this saves 8 operations. Then we observe that we can kind of change the way we think about inputs and outputs to compute our transforms on scaled inputs. And this saves us 6 operations. And then our last observation uses the linearity of the Hadamard transform to basically make the first 2 observations work, because the 2 observations on their own don't work without some extra tricks. And when you do the math, the basic arithmetic, observations 1 and 2 together brings our operation count from 37 operations down to 23 operations. And this number 23 will show up later in our operation count. In our final runtime for our algorithm. So let's go through these observations and talk about what they are and how they contribute to the final algorithm. So the first observation, reusing intermediate computations, is quite simple. Here on the slide, I have this basic example. Let's say we want to compute a plus b plus c and a plus b plus d for some numbers a, b, c, and d. Method 1 is to just directly compute our 2 sums. So m equals a plus b plus c, n equals a plus b plus d. And if you just do this directly, we get 4 operations. But method 2 here is a much faster way, well, not much faster, but it is like a slightly more clever way to do it, where you just first compute a plus b and store it in some variable, let's say k, and then you use k to compute m and n. So this way you save on doing the a plus b operation twice, because you don't need to do it twice. When you do it once, you already know what the value is, and then you can just use that value in future operations. So this is the first observation, very basic. Just reuse some computations that you've already done. And all algorithms that I mentioned before already use this kind of trick. Observation 2 is a little bit more nuanced, and it's that we can redesign the way our algorithm is structured by observing that scaling inputs can be advantageous. In particular, let h of x0 to x7 be the Hadamard transform on a length 8 input. We can define a different transform here, which we will call h star, where the Hadamard transform on our original inputs is equal to h star on the same inputs, but all except the first input is actually multiplied by 2. And we won't go into detail with what exactly h star is, but it turns out that if you ignore the times 2 operations for now, then h star is actually can be computed with fewer operations than h. So the idea here is, instead of being given the inputs directly, if somehow the inputs were already scaled up in certain ways, we can actually compute our transform more quickly. But of course, you can't directly. So actually, this H star is exactly the algorithm which requires 23 operations to compute. But we can't just say, oh, like ignore the times twos, because that's just not how it works. Somebody has to do this work. And the last observation is basically how to take care of these times twos and collect them together and do them efficiently. So the last observation takes advantage of the linearity, the fact that the Hadamard transform is a linear transformation, and it allows us to group these times twos in a advantageous way. So after the first two observation, the scaled inputs, oh, right. So these inputs here are actually just scaled versions of recursive calls because remember, this what we're showing here on the screen is just one layer of like a large recursive tree. And these x0 through x7 are going to be the results from recursive calls. So the scaled inputs were outputs of some recursive call. And right now, before applying observation 3, our algorithm is these 3 steps. We first split our input into eighths and recursively compute the Hadamard transform on those pieces. And then for all except the first recursive piece, we multiply everything by 2, and then we compute H star. But the linearity of the Hadamard transform allows us to, it gives the fact that scaling the outputs of our recursive calls is the same thing as scaling the inputs to those recursive calls. So 2h of x is actually equal to h of 2x. And this is just a property of linear transformations. So we can do what we will call pushing the times 2 operations down the recursive calls, if you imagine recursive calls being like going down a recursive tree. And we can do all these times twos kind of at the very beginning instead of at every single layer. So instead of computing h of x recursively and multiplying some of them by 2, what we do is we split the inputs into eighths and we recursively compute h of 2x on all the pieces except for the first one. And on the first one, we just compute h of x normally. And then, so after this one step, we have the exact same result as the 2 steps in the old algorithm in the before applying observation 3. And then we can just compute h star as before. Now, as we continue to like push down these times twos, we do it through every single recursive layer. So at this recursive layer, we call h of 2x. And on the next recursive layer, we're going to call h of x and h of 2x as well. But by then, some of the computations, some of the inputs will have been scaled by 4 times because it's scaled by 2 twice. And the intuition here is that every time we combine 2 times 2 operations into a single times 4 operation, we save some computations. And then this continues as you get deeper in the recursive tree and we get like larger and larger powers of 2 that just accumulate all these operations into one. And multiplying by one very large constant is just better than multiplying by a small constant many, many times. We save operations that way. So here is the final overall pseudocode for our faster Hadamard transform. We first take our input of some vector x in a field of length n, the vector's length n, and we multiply every single input by some power of 2. The power of 2 will depend on the index of where you are in your input. You like index your n inputs and just figure out which input you multiply by what power of 2. And then you plug that into h star, basically. You recursively compute h star on each piece, and then we use 23 over n over rate field operations to combine the pieces. And this 23 is the 23 that appeared before. And this way, again, we managed to accumulate all of our times 2 operations to be done at the very beginning on the entire input. And all those times 2's go into the lower order term in our final runtime, which is 23 over 24 n log n plus 13 over 12 n field operations. Notably, in many architectures and many computer architectures, multiplying by a power of 2 is actually faster and better than multiplying by a general real number, or because of bit shifts, you can just like, shift the bits around. And this extra speed is actually not covered by the runtime that I have written on the screen, but we believe that um, taking advantage of bit shifts will reflect an even faster runtime than is just being shown in the theoretical, like when you count the number of operations. And that brings us to the discrete Fourier transform. So first off, what is a discrete Fourier transform? For an input of length n of complex numbers, we define the nth primitive root of unity to be the thing on the screen. It's just the nth primitive root of unity. And the DFT of x is just multiplying the input x on the left by the Fourier matrix. And the Fourier matrix is just f of j comma k, j, k indices into the matrix is just your root of unity omega to the j times k power. And here we have an example 8x8 Fourier transform. So before we talk about algorithms, we need to talk about how we measure complexity in fast Fourier transforms. And this is a standard way to measure across all FFTs. The standard is to count the number of real valued arithmetic operations. So for example, if we want to multiply two complex numbers together, here a plus bi times c plus di, in red, we show like how you do it. And every single operation in red is a real operation that you have to do. So to multiply two complex numbers, you actually have to use 6 real operations. But this is in general. If any of A, B, C, and D are 0, 1, or -1, the operation count goes down significantly because for any of those special numbers, 0, 1, and -1, multiplying by any of them is considered to be free. And actually, a lot of Fourier transforms take advantage of this fact by trying to like advantageously group things together to get some of these to be 1 or -1. And for those of you who know what it is, this actually directly does correspond to the arithmetic circuit over the reals of the Fanon-2 model if we think of complex numbers as pairs of real numbers. So the most basic algorithm that people are probably most familiar with is the Cooley-Tukey algorithm. It is the classic, most well-known, and we can see here that it makes two recursive calls to subproblems of half the size, and then it just adds and subtracts those results together. But this was quickly improved on by what's called the split radix algorithm. And this 2-4 structure is considered the better recursive structure, and it's actually what's widely used today in the modified split radix algorithm. Our algorithm also uses this 2-4 recursive structure, where instead of making 2 recursive calls to subproblems of half the size, we make recursive calls to subproblems of half, quarter, and quarter the size, and then quarter of the size. And here we, on lines 6 through 9, then combine our recursive calls. And it is these lines 6 through 9 that we are going to talk about in improving our FFT algorithm. And I just want to first note before changing slides that lines 6 through 9 depend on the values A, B, and C. But we can rearrange the computations in those 4 lines to rely on B plus C and B minus C instead of B and C. And so once we compute B plus C and B minus C, we can completely ignore B and C and just use B plus C and B minus C. And this rearrangement comes at no additional cost, importantly. And similar to the idea of the Walsh-Hadamard transform, we can use the linearity of the Fourier transform to get that B plus C and B minus C is just DFT of x1 plus DFT of x2. And then that addition can be moved into the transform. So we can call DFT of x1 plus x2 and DFT of x1 minus x2. And similarly to how we were grouping powers of 2 together, here we're going to take this Hadamard looking structure of x plus y, x minus y, and when we push down through the recursive calls, this is going to allow us to collect a bunch of very large Hadamard transforms. And we do all the adding and subtracting first altogether in these Hadamard transforms. Specifically, when we do all this pushing down, we get something that looks like this, what we call an H prime matrix. And the H prime matrix here is for the 32 by 32 discrete Fourier transform. We end up with a direct sum, essentially, of Hadamard transforms. And this H prime actually partitions the input. Every index from 0 to 31 in this example is part of exactly one Hadamard transform. And in this picture, I've highlighted one such transform. This is a 4x4 transform on 4 of the indices. And now that we've done this factoring of H prime, this gives us our final FFT, which we call the WUFT, which stands for the Walsh-Hadamard uprooted fast Fourier transform. The H prime, factoring out the H prime gives us something with complex constants times H prime times X. And this something with complex constants is just whatever's left over after doing the rearrangement that we talked about before. And now we use our faster Hadamard transform to speed up the computation of H prime to get an improved FFT. And the details are in the paper, but this works out to 15 over 4 n log n plus lower order terms as our runtime. And this reduction that we found using H prime is actually fully general. And here we have a lemma that we state in our paper. Our reduction allows us to plug in any runtime for the Walsh-Hadamard transform to get a corresponding runtime for a fast Fourier transform. So suppose we have a Walsh-Hadamard transform and we can compute it in C n log n time. Then we can compute the DFT of a vector of the same length with 2/3 C plus 28 over 9 n log n operations plus lower order terms. And this, again, is fully generalized, not specific to our methods. And if you plug in C equals 1, the folklore Walsh-Hadamard transform, you actually do get exactly the runtime of the algorithm before our improvement. And due to this lemma, any improvement to the runtime of the Hadamard transform corresponds thus to an improved Fourier transform. And so that is it for this talk. Thank you so much for coming. I think I went a little bit over time, but I hope that is not too much of an issue. Yeah, thank you for watching this talk and have a nice rest of your day.